Today we'll be looking at this paper. So just to recap, yesterday, last class, Shayan did the same thing. We did decremental reachability, but we had a randomized algorithm which gave it was a Las Vegas algorithm which had a total update time of O of mn. Las Vegas, we had a query time of constant query time. And the updates over the entire sequence of deletes was order mn. This is what we saw. So today we'll have the same thing. We'll have a deterministic algorithm. Like today and tomorrow, we'll get to a deterministic algorithm for directed graphs reachability. That's called transitive closure. Query time will be order 1, and the total time will be order mn, and will be deterministic. Okay, that's what we'll be looking at. So this is a paper by Jacob Lucky. Okay, fine. Okay. So first we'll start with the same problem but restricted over DAGs. Okay. So, and in particular, we'll start with single source reachability on DAGs. Okay. So what is a naive algorithm you'll have? Each time you delete an edge, you do the entire O of m reachability. You have everything. So that's order m squared and constant m query. Okay. So naive query of constant and update is order m squared each. Order m squared total. See? This is the naive thing. So we'll improve this to order mn. Sorry, we'll improve this to order m. Okay? So this is what we'll be looking at right now. Order m total time. Order m total time. This is for single source reachability. We'll do it for in order m total time. And we'll just use this and use this on every vertex. So that's order mn transitive closure. We'll get to that after this. Okay. Fine. So, fine. So we'll directly jump into the algorithm for this. The algorithm is actually pretty simple. Yeah.
One question. You will get mn total update time for transitive closure.
Yes.
Even for transitive closure, but the title of the paper says strongly connected components.
No, a strongly connected component is the next part. Right now we're only looking at DAGs.
Okay.
Right? So particularly on DAGs, we just look at reachability.
Okay.
We'll get order mn total time, and we'll use this for general graphs, and then we'll get to SECs in between. Okay. Yeah. So again, okay. So what is the problem now? You are given a DAG D E comma E. You have a particular vertex. Okay. Call it S, and you have a series of updates. Delete of u comma v. So this is directed. Directed as cyclic graph. And the query is query of u comma u. Query of u is u reachable from S. So this is what we want to store. So initialization, you're given a some random vertex S in the DAG. So given that this is a decremental algorithm, okay, so the entire next 2 days will be only decremental. We won't be looking at anything apart from this. So given that it's decremental, anything which is not initially reachable from S is never reachable. So we'll just do a order M DFS from S and just get the initial reachable vertices. Okay. In it, order M, get all reachable vertices. Okay, so throw away the remaining vertices. Okay. And given that this is a DAG, can S have any incoming edges? After doing this initialization, can S have any incoming edges? It can't, because if I have S, suppose I have an incoming edge from U, I know that U is reachable from S. Otherwise, I would have deleted U, but I can't have a cycle, so this can't happen. So after this initialization step, S is a source. So terms, source is a vertex which does not have any incoming edge. Sink is a vertex which does not have any outgoing edge. Okay. So S is a source, and there can be multiple other sources. Okay. So let's say S1, S2 be some sources. S1, S2 to SL.
If there are other sources than S, you can't go from
Yeah,
S to S.
exactly. So right after this initialization, we see that there can't be any other sources, because like from a source, that can't be reached from S. That's simple. So right now, this L is 0 after the particular initialization step. Okay, fine. So now you delete some vertex UV. Okay, then what can happen? Say I have a S. Suppose I delete this UV, I have other things here. Suppose I delete UV. What can happen is V can become disconnected from S, and things reachable from V can be disconnected from S. So it's only V and the reachability of V in a way. Okay? And not the entirety. Not every vertex reachable from V need not be disconnected. Say there was a vertex like this, then this vertex is still reachable from S even after removing this edge. So it's a subset of the vertices reachable from V. Okay, so this is. So now we look at a somewhat more general problem as a subproblem, and we'll get to this. So that's a problem is called downward reachability. Downward reachable of D. Okay, so we'll get to some algorithm, and in that algorithm, in the intermediate set, in any intermediate step, you might have other sources. S need not be the only source. Okay, so let the other sources be in a set called SO. Let SO be the set. No, let's not have SO. SR. Let SR be the set of all sources except S. Okay, so I have this function downward reachable which has this DAG, and it has the special source S, and it is also given the entire set SR. Okay, so an overall view, what we are trying to do is, I have this DAG S, I have other sources here. Okay, now I want to find all the vertices which cannot be reachable from S, which can't be reached from S. What is the naive thing again you'll do? You'll start from S, just do a DFS, get to all the vertices which are actually reachable. And then just a complement, that's the vertices which are not reachable. That's fine. But what we don't want to do is we don't want to go through all the vertices which are reachable. That is a lot of time. So think of it this way, in the decremental algorithm, each time we delete a vertex, some vertices get disconnected. We want to spend time only proportional to that. We don't want to spend time proportional to all the reachable again and again. Because that's like the kind of high level intuition. So that then we'll kind of amortize over that and just add up and it'll come to be nice. So what we now want to do is we want just the vertices which are not reachable from S. Okay, we want to output all those vertices in time proportional to the number of vertices and the number of edges incident on them. We will get to this formally, but this is kind of what we'll be hoping for. So that's why we do not do the normal reachability from S. So, okay, think of the algorithm, I mean, like when deleting a edge UV, we know that V is the culprit. So we actually have the next source. So that is kind of the intuition behind having this, I mean, with intuition of assuming that we have all the other sources as well. Okay, so I'm just like jumping forward, but I'm just, yeah. So this is the function we want to get. So this is, we have a DAG, we have a particular source, and we have the other sources, and we want to find, so this should return a set, a pair u comma I, where u is a set of nodes which are not reachable from S, and I is the set of edges incident on U. Okay, all the edges which have at least one endpoint as U is I. We want to output all of these. So what is the high level idea? I mean, we'll find this, we'll delete U, and we'll delete all the edges incident on them. But to find this, to find U, in a way we'll do some exploration, which will take time proportional to I.
So I denotes the set of both incoming and outgoing.
Yes. Any edge which has at least one endpoint in U is an I. So we'll be aiming for a order of U plus I algorithm for this. Okay. So just think for like some few seconds. I mean, it's some pretty simple thing. What do you want to do? So what are some vertices that are guaranteed to be in U? Like straight away, what do you know?
So if you're deleting u comma v, then if v does not have any incoming edge, then
U comma? No. So right now, forget about deleting any edge. So this is a abstract subproblem you're looking at. So this subproblem, there's no deletion or anything. You just have a DAG. This DAG is not a single source DAG. It has multiple sources.
then the other sources are in u.
Exactly. So the other sources are in U for sure. So, okay. So we know that the other sources are in U. So now you can delete them. Delete their edges. Exactly. It's as simple as that. So did you understand what he said? He said, you take all the sources, delete them, delete all the edges going away from them. They don't have any incoming. Now check if there is some other new source formed. Okay, so let's write that down.
What is the goal for this algorithm?
This algorithm should return U comma I, where U is a set of nodes which are not reachable from S. There'll be, so in this graph, say this is S, all these are reachable, so there's no deletion. Like forget about deleting edges. All these are reachable from S. There are some other nodes here, S1, S2. There are some nodes, and this might connect here. So now these are sets of nodes which are not reachable from S. We want to output all of them. So the algorithm is as follows. Okay. So you have a kind of a queue or a set, it doesn't matter. So this queue will, the invariant will be, this queue will contain all the sources of the current graph. Okay, contains so initially you can set Q to be SR. Okay. So sources except S, sorry. Okay. And you set I to be empty, U to be empty. Now you loop over every element of Q, okay? While Q is not empty. Take the first element from Q. Let that be, I don't know, V. Okay. So now you know that V is a source. Okay. So now this should be added to U. So as simple as that. So U to U plus V, U union. So now, suppose you delete this source, you can delete all its edges. Take all the edges incident on U, add it to I. EV is the edges which are incident on V. Okay? And you delete these edges from the actual graph itself. Yeah.
Arrows should be the other directions.
Oh, sorry. Yeah. Okay. So now you deleted these. Yeah, exactly. So now each time you delete this edge, suppose you are deleting V comma X. Then you check if X is a new source. So what you do is you have another array which has the number of incoming edges of every vertex, in degree of every vertex. And each time you delete a in edge, each time you delete Vx, you just decrement the in degree of X. And if the in degree of X becomes 0, you know that you have a new source. Add it to Q. Okay. So if in degree of X minus minus, if in degree, if it is 0, then add X to Q. Fine. So this is all that is there. So is the algorithm clear? You start with all the sources, you add it to a queue, and you keep taking one of them, deleting the edges. And each time you find a new source, you add it to the queue, keep repeating this until the queue ends. So now, why does this give us U and I?
Basically, if you delete an edge U comma V, if the V
U
does
comma
not
U comma X.
delete-
Fine.
No, I mean in the normal
Okay.
this problem.
Hmm.
If you delete U comma V, V becomes a source.
No. For now, let's forget about deleting edges. There is no deleting edges in this subgraph, in this subproblem.
No, after this problem,
Yeah, so now we are still looking at the correctness of this algorithm. It's not clear yet. I mean, do everyone see why this is clear? It's somewhat easy only. So there are just two things we need to prove. We need to prove that every vertex that we add to I was actually not reachable from S, and every vertex not reachable from S is added to I at some point, right? So we'll do the one direction first. Yeah?
I mean, I can see how it fits into the decremental reachability thing.
Right.
But as far as the specific subroutine is concerned,
Mhm.
when the subroutine is called, what is the status? That you have a set of sources SR
Yes.
other than S.
Yes, and we know that that's given, like, yeah.
Yes.
We don't look at how we compute that we look at it later.
And we are guaranteed that every node other than SR is reachable from S.
No,
You need this-
there is no guarantee. That is what we are
Not
fighting.
guarantee. Okay.
No.
Sister, you're trying to prove the set SR, right?
See, we are given a DAG. This S is the initial source we are looking at. That is constant always. And this SR is the set of sources which are not S. I mean, the set of other sources.
I see. Thank you.
Yeah. Now we need to find the reachability set from S.
But we will know that everything. So if something is not in the subtree of the source, then it is
Sure.
reachable from S.
Yeah, but we do not want to find the subtree of S because we'll spend time proportional to that subtree.
Delete, all those vertices.
Yeah. So we know that we will need to delete these, so we want to spend only time proportional to those which we delete, not the complement. That's the whole idea. Okay. So what we'll want to prove is if V was added to I or U, sorry, U. Then V was not reachable from S. So there's a proper formal proof using induction. We'll not get into the actual form. We'll just look at why it's done. If V was in the initial sources, then it's deleted. We are fine. That's not a problem. Okay. Otherwise, V was added to the queue at some point. Why was it added to the queue? It was added because it didn't have any in degree. Its in degree became 0. That is, all its incoming edges had been deleted. But why had they been deleted? It's because every parent of V had been deleted, and when they were deleted, its edges were deleted. And kind of like induction, whatever was deleted was already not reachable from S. So none of the parents of V were reachable from S. So V is not reachable from S. Okay, it's like a variant. I mean, like invariant. You just keep an invariant. The invariant is basically whenever we delete a vertex from whenever we delete the vertex V, this vertex was not reachable from S. This is the invariant. For the initial SR things we delete, that's clear because those were sources. Now after this, you just use this invariant and prove that it can't be done. So this is clear. Suppose V was not reachable from S. We'll need to prove that this was added to I at some point, U at some point. So any guesses?
So if V is not reachable, then none of its parents are reachable.
Okay.
Then none of their parents are reachable.
Okay.
So you know
Continuing like this, we'll come to a source.
either B is a source or
We will reach a source because
Yeah.
all other vertices which are not in the
Even
subtree of
from-
the source are reachable from this.
so you'll be added to Q at some
No.
point of time.
Yeah.
So we will be added to Q at some point of time.
No. How do you prove that? That's the point. How do you prove that
What is your statement? V is not reachable.
V is not reachable from S at the very beginning? So let's call this D, and at the end of this algorithm, let's let the DAG be D prime.
So
Whatever you're saying, are you saying in D or D prime?
what I'm saying is if V is not reachable from S, then V must belong to the union of subtrees of those other sources.
Okay. That doesn't. I mean, even if V is in a sub.
Now we do this argument that if V is not reachable, then its parents are not reachable.
Yeah.
Their parents are not reachable.
And then finally you get to
We
this.
have to reach those
Yeah.
sources. We can't reach anything.
That's.
So the sources exhaust all the vertices, right? Isn't it right? Or else
The
V is a
sources
source,
union S
basically,
exhaust
right?
all vertices. I mean the
Yeah.
subtrees of sources union the subtree of S exhaust all
Yeah.
vertices.
Okay. Another way to see this is look at D prime. D prime has only one source. It's a single source DAG. D prime is the DAG after this entire algorithm is done. Why is this? Because initially all the sources were added to Q, and after this, whenever we create a new source, we add it to Q, and whatever is added to Q is deleted. So at the end of this algorithm, there are no sources apart from S left. So D prime is a single source DAG. Now take V. Look at the ancestor chain of V. Like just go up. you'll have to hit a source at some point. And that source can only be S. Because this is a DAG. See, take V. Okay, at the very beginning of...
D prime, if V is remaining in D prime, then V's ancestor,
Yeah.
like topmost ancestor has to be S.
Has to be S.
But
He
then
is
that
in
is
D
not
prime,
possible.
then that is not, you are not even starting, I don't understand, I think it's.
Proof by contradiction.
No,
Suppose V
okay,
is
so
remaining in the graph.
So what I want to prove now is if, suppose V is not reachable from S, then I want to prove that,
V is not in D prime. Yeah.
yes. Assume to the contrary, if V is in D prime, just look up, there will be S at some point, which is contradiction. Fine.
If it's not, then you will be deleting V.
Sorry? Yep. So this is also proved. So the correctness of the algorithm is fine, right? Whatever V is exactly the set of vertices which are not reachable from S. And I is just the incident edges. That's also fine. That's somewhat not clear. You need to... Okay, so basically here this EV will be the set of outgoing edges, right? Because the incoming edges are already deleted. So at every point we add the set of outgoing edges from every vertex, but an incoming edge to a vertex which is deleted would have been the outgoing edge of some other source that would have been added. So induction. So the correctness is fine. So now what is the running time?
So mostly,
Yeah.
I will only have
I has any edge which has
outgoing edges,
No, no, no.
right?
no.
So incoming edge of some vertex is outgoing edge of some other vertex.
But that will already be in you.
Exactly. So it would have, that edge would have been added. See, okay, see. I have a vertex V. Okay. All its outgoing edges constitute EV and they are added to I at this point. When I delete V, I add all its outgoing edges because it didn't have any incoming edges. But take an incoming edge. The claim is this incoming edge would have been added to I already because I would have looked at this vertex and I would have deleted it. So I contains all the edges which are incident on any vertex on V. Fine. So now what is the running time of this algorithm? How many vertices are added to the queue? It's exactly mod u. So the while loop runs mod u times. And this loop, deleting every edge, is I look at every edge in I exactly once. Yeah, exactly once. So the running time is order of mod u plus mod I. Okay. So in this much time, given, this is important, given the other sources, I can find the entire reachability graph. For the sake of like future, I mean like we'll use this subroutine in a slightly different way, and I'll just say what that is. So instead of giving all the sources, we'll be given some set S prime of vertices, and we'll be guaranteed that all the sources are in S prime. This is the guarantee we'll be getting. We won't get the exact set of sources, we'll be getting some larger set, but then this can be checked in mod S prime time. We just loop over all vertices and see which are the sources and just take those sources. Fine. So in mod S prime time, we just find the actual set SR and then go through this entire thing. So the running time is mod S prime plus this in this thingy. Okay, sorry. So this subroutine we'll be using in a slightly generalized form. That is, we won't be getting the exact set of sources. We'll be getting a somewhat larger set, S prime.
Check whether it has
Yeah.
degree 0
Yeah.
and then
Exactly. If it is, then add it to SR and then continue the subroutine. So it's S prime plus S.
If we have an array which shows all the integers of the vertices,
Hmm.
what is the problem in finding the exact sources? We know which are the sources, so we can see from
Yeah, we don't want to loop over all the n vertices.
okay, but you want to go over this
S prime, whatever is given to us, we just want to loop over them. Okay. So analogous to this, we have another subroutine which is upward reachability. D comma S comma Yeah.
Doesn't this subproblem directly solve the main problem?
Yeah, it's almost done. Just some 2 lines. Yeah.
So because
Main problem isn't for
I
DAG.
understand S prime also because if a UVH is deleted,
Yeah.
if V is the same, just pass V to this.
I know.
thing.
So this subroutine is, we'll be using the subroutine in a more general form, not just for DAGs.
Okay, so for later.
Even for general graphs, we'll be using this. So we don't even need I. What is I doing here?
Yeah.
Okay. So the other subroutine we'll be looking at is upward reachable, which is you're given DAG, you're given the source S, the same source. This source is constant everywhere. And we're given the set of sinks. Okay. Okay, sorry. This source is not a source, this is a sink. You're given some particular sink. Okay, and you're given the rest other sinks. And now you want to output u comma I, where u is set of vertices from which sink is not reachable. Let's okay, what is this? Let's just call this S. Okay, I'll call it Si. Okay, S prime. Fine. So use a set of vertices from which S prime is not reachable. Okay, so it's like the, so this downward reachability was S and all the set of vertices which were not reachable, and S is the set of vertices from which you can't reach this sink. So it's exactly the same. I mean,
You do this in GR.
in GR, yeah. So this can again be done in this much time. Okay.
Why is the set of edges different from
Sorry. And we have another subroutine. It's called just reachable. Okay. So I'll just say. So, in the general graphs or even in DAGs, it'll be very clear from the context what this S and S prime are. We'll have one designated source and one designated sink. Okay. So just notations, we just call upward reachable of D, and it'll be clear what S is. Downward reachable S. And we'll take the union of these two and get those vertices which are either not reachable from S or don't have a path to S prime. That is called reachable. So I'll get to this when we do that. I'm just giving a heads up right now. It's called reachable of, yeah, this is reachable of D. Fine. Okay. So armed with this, now how do we do reachability for DAGs? Yeah.
So this procedure does not require maintaining an explicit reachability tree at all.
No.
It can just maintain the collection of the
Exactly.
vertices.
Yeah. All I need is just the adjacency lists and an array which tells us if U is reachable from S. This is single source as of now. Okay. So this was, okay, again, so this was a single iteration. Fine. So now just think of DAGs and think of deleting edges one by one. How will I use this subroutine to maintain my reachability? So let's get to at least the first main subproblem you're looking at. Reachability. Okay, let's look at single source reachability. Okay, so single source is S. Okay, so initially I do this initialization. I have the set of vertices which are reachable from S. So initialization in order m time. Okay, so another thing, we always assume there is no isolated vertices. Okay, so number of edges is always greater than number of vertices. So that's always subsumed. So in order m time, we get all these. Now suppose I get a update, which is delete u comma v. So now suppose I delete this v. Initially there was only one source, s. Now there is one more source. There is potentially one more source, v. V need not be a source. I could have some other edge like this. Okay. So this is where we have this. It's not SR, we have S prime. So we set S prime is V. Okay.
Check whether V is in the
Yeah, I know. It's useful in the future using this hammer we have. So we set S prime is V and we call this subroutine. And whenever I delete this, I delete the vertex and I add it to my unreachable set, or I have a reachability array. Reachable of u is 1 if there is a path from S to u. Okay, so one more notation. This means there is a path from S to u in G. Okay, so reachable of u is 1 if there is a path from S to u. And each time I delete a vertex, I just set this to 0. Okay, so once I delete a vertex, I spend time proportional to order u plus I. I set u of these cells to be 0, and I delete so many edges. I keep doing this again and again over and what is the query? Query is just look at reachable of u and tell if it's 0 or 1. Now I do this over multiple iterations of updates because every edge I'm looking at, I am deleting. I have only m edges to delete, so the entire total time is n plus m, which is just m. Okay.
So here S prime is just 1. So in
Yeah.
general case you have to be careful.
Yeah, definitely. Even in this, S prime can grow large in a way. Okay, here it can't grow large.
S prime is basically
Yeah.
Every time you're
My Q can grow large. I mean, once I delete S,
yeah.
once I delete this, whatever V, I'll have more edges.
No,
And
but the thing is, if S prime is, I mean, like for general case, if S prime is too large, then
Okay.
this will blow up.
sure, but okay, let's get to that when we get to general graphs. I mean, see, the intuition is I know that all the sources I have to delete. So I might as well spend that much time. I can afford that much time because that will be subsumed by the order n time, right? I mean, I delete vertices only once.
No, but the point is, you may not have to delete all vertices of S prime.
Oh, okay,
That's what
yeah,
I'm saying.
that is a good
Be
point. Yeah,
careful about
sure, yeah, that's a very valid point. But yeah, but here it's not a problem. We just go over this. So total update time is order m, query is constant time. That's it basically. Yeah. So this is yeah. So this is the entire, and we have transitive closure for DAGs in deterministic order m and time, constant update, blah blah blah. Single, no. Oh right, sorry, I'm very sorry. So this is for single source in order m. So for transitive closure, you just do this for every vertex, and you just look at that. You have an array, you just look at that. So query is again constant, update, total update time. Fine. Deterministic. Okay, so this is all we want. So now we'll look at general graphs and we'll basically set up some definitions and some structures which we'll later use tomorrow to find the actual SECs. So, okay, so again a small overview. Why did we do this DAG? we'll basically get the SCC DAG, the DAG given like compressed by SCCs, and we'll use this algorithm whenever there's an edge of the DAG. And when there's an edge we want to delete inside a particular SCC, we'll recurse on that. This is like the very overall top view of the entire algorithm which we'll be looking at. And to recurse, we'll have some trees, some data structures. But yeah, so right now we'll just kind of build up to that. Fine. Okay. So some definitions. Okay. So now we have a graph G. What is it? Compress of G. Compress of, sorry. Condense of G. Sorry. So condense of G is a new graph, which is basically take the SCC decomposition of G. Take every SCC, condense it into one vertex, and that forms a DAG. That DAG is the condense graph of G. So there'll be some somewhat non-trivial examples, definitions. So I'll draw a diagram for this. Okay. So bear with me for some 5 minutes. So this is some random graph which we have. So condense of G will basically be look at all the SCCs of this. What are the SCCs of this? Yeah, so 4, 5, 6 is an SCC. 3 is an SCC. 2 is an SCC. This entire thing is an SCC, is it? Yeah, this entire thing is a SCC. Right, make sense? Okay. So the condense of this will be I have, okay, so let's get the notations correct. So every vertex in condense is labeled by the set of vertices which are in that SCC. Okay, so this is set 2. Set 2 has a edge to set 3. Set 3 has an edge to and the rest, whatever, 1, 2. This set has an edge to 2 and 4, 5, 6. So this is the condensed graph of 1 to 11 or whatever. Makes sense, right? Yeah, okay. So this is condense of G. This was G. So now we look at something called split. I'll delete that. So split of G comma D gives us a new graph D, GD, that just says take a vertex, make 2 copies of it, D in, D out, add all the in edges of D to D in, add all the out degrees of D, or all the out edges from D to D out. Okay, so let's, no, you do this for just D, the particular vertex D. So let's just take some small, suppose I add, sorry? You're given a graph G and a particular vertex D. Sorry. D is this. If this is G, if I call split of G comma 1, okay, let this be this. I'll have 1 in, I'll have 1 out, and I have 3, I have 2. 3, this goes here, this goes here, and this goes here. That's all. No, I don't put anything. So what is why do we do this? Basically, we want to convert any general graph into some kind of DAG. Okay. If at all we have a DAG, we want control over the source and sink. We don't want any random source and sink. We want to somewhat control which source and which sink we want to have. And this is a nice way of controlling it. Now, suppose this G had been a DAG. Now, I in and I out, D in and D out. D in is always a sink, D out is always a source. That's clear, right? So this will be we'll have handle on these two and we'll work with this. That's basically what we'll be doing. Okay. Fine. So what we'll do is we'll take any general graph G. First we'll apply condense, so we get a DAG. This is a DAG, right? No, this is not a DAG. Why is it not a DAG? This should be a DAG. Sorry, this is here. Yeah, this is a DAG. And we'll apply split on this with some particular vertex here. We don't care about which vertex. And we'll have handle on these two things. Okay. So what we'll actually do is, yeah. So in this particular thing, suppose we split. There's no subproblem as of now. Right now I'm just building up two SECs. There's some small lemmas we'll be looking at. So now look at, yeah. So okay. I'm sorry, it's not condense and split. We'll do split and condense. So first we split this. Take any general graph G, split some particular vertex. So we have a particular D in and D out. Now see that D in is an SEC on its own, D out is an SEC on its own. Then we'll condense it. So we'll get D in, the SEC corresponding to D in is a source, the SEC corresponding to D out is a sink. There might be multiple other sinks and sources, but we care only about these two particular sinks and sources.
How are we choosing?
Choosing one is arbitrary as of now, for all we care. So should I do this? Let's skip over. Okay, let's actually do this. Suppose we split, we do split and condense of G with respect to 1. We get, instead of this 1 here, we have, we have 1 in, we have 1 out. How are these? Okay, so 1 out goes to 2 and it goes to 7, and 1 in has an edge from 11. Okay. So now the SECs change in G. So now the main point to see is that G out and G in are SECs on their own. Okay. And now what are the other SECs? This remains the same, 4, 5, 6, 2 and 3, this is same, but here it changes. Initially it was entirety of this which was a SEC, but now it's, this entire thing is not an SEC. This is an SEC and 11 is a separate SEC. No, sorry.
7, 8 is an SEC, 9 is an SEC, and 10, 11 is
Sorry. Right. 7, 8 is an SEC. 9 is a separate SEC, right? 10, 11 is an SEC. Yeah. And there'll be this graph corresponding. This remains same, this remains same, this remains same. This will split. And we have 1 out, goes to here, 7, 8. Seven, 8 to 4, 9, 10, 11. Fine. 7, 8 to 10 also. Okay. So now this is again a DAG. Fine. Blah blah blah. So this DAG is called split and condense of G. And so you got the, I mean, like at least the top level is to get a handle. We want a DAG, and to get a DAG we just do condense, but we want to have a handle on which source and sink we want to work with, and for that we do split. That's all. Okay. So now we have the opposite of split, which is merge. This is kind of an artificial thing. So merge takes a graph G, or rather it's like ditch D. You just take a subgraph, call it H, and D. Okay. So this H could be a subset of the vertices. So now we are working in the context of every vertex being a set of vertices. So this merge will always be applied to the split and condense graph. And in split and condense graph, every vertex itself is a subset of vertices. Okay. So what merge does is it takes a bunch of these vertices, and in each of these vertices, suppose it contains a vertex which had been split. That is, if it contains one, so we kind of see this one D in and D out are special. Okay. So they're like, they're marked. It's not any random vertex. So if it contains D in and D out, it will replace that with just D. It'll replace 1 out and 1 in with 1. Let's see. Suppose I apply merge on this entire graph. Okay. This 1 out was basically set of 1 out. This was set of 1. So 1 out will be replaced by 1. 1 in will be replaced by 1. But now these two vertices, these two nodes are the same because they have the same subset. So these two will merge.
And then the whole thing will collapse, right?
Yeah, you'll get back the old condense. Not really. We'll get to that later. Right of as of now, just think of it as just. So now it's.
Then it will no longer be a DAG.
Yes, it's fine. It will not be a DAG. True.
So you're not
No, not as of now. That is what we'll be aiming for. It's not clear how to do that. Basically, what you want is you want to get condense of G from this. What you want is condense of G, right? See, we had G, we split it and then we condensed it. Now we are merging it again. Ideally, we want condense of G back, but it's not clear how to get that. We'll get to that.
So merge of H comma D.
Takes a subset of these vertices. Each vertex is a subset of vertices in G. If any of them contain D in or D out, it replaces it with D.
If D belongs to H, if D in comma D out belongs to H,
No,
then
H is a, okay. Let's do merge of,
D in and D out will always be singletons, right?
Yes, that was
yes.
question I had. That
Okay.
will always
Yeah, they'll be singletons, yes. Now H, suppose H was, I'm working with this graph, okay?
Set of
Subset of subsets, yeah. Subset of vertices in this.
Data nodes, okay?
Sure, these are called meta nodes, fine. Okay. So now suppose H contained this, this, and this. What H will do is just replace this with 1.
Oh, it won't read.
It won't replace that. Whatever is there in H, it will go to every node, replace it with 1. Replace D in or D out with D.
If D in is in H, it will replace.
Not in H. If D in is in a subset of H, D in is an element of H.
Yeah.
Yeah,
So if D is an element of H,
it will replace that with D.
by D,
Yeah,
D out is an element of
it'll
H.
replace it.
So both
And
are
now
H,
if
both are-
two nodes are same, like suppose one in was also in,
then you have two D's, so you merge.
it's merged, and you get the same thing again.
But if D in or D out neither is in H,
You don't do anything. You'll remain the same.
So if you want to actually get G back, I mean condense of G back, you can do downward reachability from one out and upward reachability from one in and take their intersection and merge them.
Come again. You'll take
Downward reachability from one out,
yes.
I mean take the U of that
Hmm.
and take upward reachability from one in
Intersection.
and take their intersection and merge them.
Yeah, but we don't want to spend that much time.
Yeah.
Again, we'll do something somewhat better. Okay, so let's merge. Is there any other definition? That's all. Okay. So I'll erase this. So leaving these things aside, one more somewhat smaller overview. What we have is, okay, so let's look at the entire picture. What we want is to have transitive closure for any general graph. So first we decompose it into SECs. Now each SEC is independent of each other because it's a decremental algorithm. So we, as of now, have a SEC. So we have a component which is SEC. Now on SEC, we do split and condense. So we get a bunch of SECs. And we have this graph. Okay? So basically because once you do split, the graph is no longer an SEC. That's clear. I have G. G had is strongly connected. I do split of G with some random node D. Now this cannot be strongly connected because from D out I cannot reach D in. So this is not strongly connected. So the condensed graph of this graph has at least two vertices. Some blah blah blah. So now I maintain, sorry? Yeah.
I have at least 3 D's.
Really? If it's a single vertex, I have two vertices. Yeah. So I maintain this DAG and I look at updates. If I have a delete, so okay, so another thing, in this DAG, I have each vertex, right? Each edge. Okay, I'm very sorry. If I have multiple edges between components, it's not given here, is it? Okay, initially, before splitting, so before splitting, we had 1, 11, 10, 9, 7, 8 as one SEC. So there were, okay, suppose there had been an edge from 6 to 9. Okay, so we have multiple edges between two SECs.
I mean 9 to 6.
Yeah, 9 to 6.
There is
Probably
9 to 6. Or just say I have 7 to 6.
yeah.
Okay, so I have two edges from 7, 8 to 4, 5, 6. I keep double edges. So I keep these multiple edges. I forgot to say this. So let's not have this for now. Yeah.
So there are two different problems, right? One is just maintaining the strongly connected components.
Yes.
The other is maintaining the
Transitive closure. We'll be going to that through this.
Yes. So if you just want to maintain strongly connected components,
Okay.
then you don't need to keep these double edges, right? You don't even need
Uh,
to maintain this meta DAG.
No, we'll need to keep. See, the purpose of having these double edges is, suppose okay. Yeah, sure. If I just want to maintain SEC, I don't need the double edges
Yes.
because I'll only be interested in decomposing SECs. The connection between SEC, I don't matter. No. Sorry. No. So because this entire graph is not the actual graph. We've split it. So even if it's still not clear what the actual this entire thing is an SEC.
Okay.
These are like weird SECs inside that. These are artificial SECs. I still haven't given you like intuition into what these are.
You just need the reachability of one SEC from the other. So why do you want multiple edges?
Because if I had two edges and I delete one, then it's still intact. But suppose I had only one edge and I deleted it, now the SEC might change.
okay.
You reach it only when there are multiple edges.
No. See, suppose you don't have multiple edges.
Oh, okay.
Now, let's just take the algorithm you're saying. I do at that point. Okay.
So my question is, if we just for the time being concentrate on strongly connected components,
Okay.
the things that you were right now saying, will they still be required while maintaining just strongly connected components? Or
Yes.
This can be simplified further because conceptually it will be easier to think of these two problems
No,
one after the other.
we'll need it.
Sorry?
We'll need it.
We will need it
Yeah.
even for strongly connected
Yeah.
components. Okay.
Just maintaining SECs will need this.
Even this D in, D out business, split and contents.
I mean, if we're going in this direction, we'll need this. I mean, there might be some other totally different approach to maintaining SECs, but at least this approach we are taking, we'll need this. See, basically because D in and D out are there, we'll need this multiple edges. If we had not split it into D in and D out, then we won't need this. We won't need the connection between SECs.
Okay.
Because this entire thing, we know that in the actual graph, this entire thing is a particular SEC. It's just one huge SEC. But now we have this artificial split up of this. We like artificially modify the graph, and in this modified graph, we are looking at the SECs.
Okay, one second. If the original graph was an SCC,
Mhm.
then after you perform one split, the thing that you get, there will be just 3 components in it. Isn't it? No. There can be more components. I mean,
For instance, this SCC, this 1, 7, 8, 9, 10, 11, broke into some 5 things. So if that would have been the original graph, then you would have 5.
So what we do have is that there'll be only one sink and one source.
okay. The only thing that you know is there is one sink, and why
One
can't there be more than one source?
Because we know that if this entire graph is a SCC, I'm jumping
Oh,
ahead.
So it must
from D,
be
you can
reachable
reach
from
Exactly.
D out.
Everything is reachable from D out. Everything goes to D in.
Okay.
So we'll get to the structure of this split and condense graph later. I mean that's like the main part of
Putting an
what
edge
we're doing.
between D in and D out will make it a cycle. So
Yeah, which is not what we want.
Okay, okay, fine.
What was I doing? Oh, right, the overview, right. Okay. So, so we have this SCC. We split it, then we condense this. So we have this DAG right now. Now notice that every edge here, even if a double edges, every particular edge corresponds to an actual edge in G. The edge from this component to this component was actually this edge and this edge. So there is a one-to-one mapping between the edges of split and condense G, and not one-to-one, an injective map from that to this, that to this. Whatever, yeah, subject, yeah, you get the point.
Yeah, an injective from
This, okay. So suppose I get updates. My updates are on G. I want to delete some edges in G. Now the whole point is, if this edge is in this DAG, then we use the algorithm we have for DAGs. We already have a decremental algorithm for DAGs.
what can you
We get an update, delete this edge UV. Now we see if that edge is an edge in the split and condense. I mean, this is not what we do. I mean, this is giving some very overview.
Otherwise, you will recurse within.
Exactly. Now, if this edge was here, then we apply the algorithm we have for DAGs and just do it. It's not clear what the running time is. It's not.
No, it's not about the running time. So how do we choose D to, I mean, which vertex?
It's just arbitrary. As of now, it's arbitrary. Suppose we've done this, but suppose this edge was not an edge in connecting these different SCCs, then it should be inside this. Now each of this is an SCC in this graph, so we recurse on that. So this recursion is through some SCC tree, which we'll come to tomorrow. That is,
Recurse and then split a vertex and then.
yeah, again we split a vertex, do that. How we exactly split, we'll come to those things later. But yeah, so, okay. So one more, yeah.
I have one other thing. Consider this following problem. Initially, you start with a strongly connected components. Edges are deleted after one after another. And you just need to report at what instance
Exactly.
it does
It
not
does not
remain
become a-
strongly
yes.
connected. It's an even easier problem,
Exactly.
right, than maintaining this. For this easier problem, do you get O of m update time, or the update time is still O of m?
So what we are building up is to exactly what you're saying. We'll have that. This is what we want, but we'll have a somewhat more generalized algorithm, which we'll use for further uses. But this is as of now the main purpose of doing what I'll do today is to solve your problem.
Okay.
To-
but my
I-
question
okay.
is, even for the
Is-
easier problem,
is
you
there
get
a
the
better-
same bound of
I
m,
do
or
not know.
you get a better bound?
I'll have to think. Let's see. From this using, I mean, like if we split, we'll need this mn. Whatever we are doing right now will I don't think it can be approached. I mean, there might be some totally different approach, but once we do split and condense, I believe what we're doing right now is kind of what we have to do. But yeah, okay. So what he asked is exactly what we are going to. So we know that this entire G is a SCC, is strongly connected. Now we delete edges one by one. We want to know, when does this SCC decompose? When does it break down? So we're looking at G, not at some particular thing here. It's two different things. Okay. So keep this in the back of the mind. We'll come to this at some 10 minutes probably. But right now what we'll do is something more general. So now we look at the structure of this graph. Okay. So these were this was source and sink. Okay. So we have a couple of claims here. What we first do is we call downward reachability on this, let's call this G prime for now. As Abhratanu suggested, we call downward reachability on G prime using this as the source. Okay. So we get a set of vertices of G prime which are not reachable from S. So those cannot be in the SCC of G.
G prime is when you have split and condensed G.
Yeah, G prime is this graph which is split and condensed.
But then one out will be the only source.
One out is need not be the only. I mean, if G is okay, if G is strongly connected, then this is true. We are like loosening that constraint. Now it's any general graph G. Okay. Okay. So that's one more thing. I mean, that is clear, right? If G is an SCC, then one out and one in are the only sinks, and so it's the only sink is the only source. There can't be anything else. We proved that, right? Okay. So what was you saying? Right. So I have G prime. I call downward reachability on G prime with D out. This is the vertex with D out as the source. Okay. So now in some time, we will not analyze what time it is. It'll return us a set U comma I. Fine.
And what are we supplying as the list of sources? We are just supplying the source.
Oh, very good point. Yeah. So that source is just one out, right? D out. Okay. So right now just D out. We have that also in hand. So we supply S prime or SR depending on, let's just say we have SR as of now. So in this graph, we also know the set of sources. We supply that and we supply D, and it tells us which are the vertices which are not reachable from D out. Okay. That's U. So now the claim is U is a set of sets, subsets, right? Take the union of them. Union of U. Okay. So okay, let's actually do this. What are the vertices in G prime which are not reachable from one out? This is reachable, 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 reachable. Oh, everything is reachable.
It will happen after you delete it.
Yeah. Okay. Right now it's of course connected. Okay. Suppose I deleted this. Suppose this wasn't there. Then a set of vertices which are U will be this, and this. Right? So what I mean by union of U is just the set containing 7, 8, 9, 10, 11 and 1 in. Okay. I take that. I take union of this and I merge this. So what was merge? If at all there is any 1 in or 1 out, replace it with 1. So there is a 1 out, 1 in. So I'll replace this with 1. So after doing this, this set is basically 1, 7, 8, 9, 10, 11. Okay. So
Okay. This is the merge.
this is merge of union of U.
No. The merge had two inputs, right? So the first one was the set
Um,
of meta nodes. What is the second input? Is it one out?
Oh, sorry, that's 1. Yeah. So that we will always mostly ignore because it's clear that 1 in and 1 out are the only special nodes, and that will be merged into 1.
Merge has to be supplied a subgraph.
That subgraph is union of U. It need not be a subgraph. It can be just a set of vertices. Okay, keep it as just U. The notation is very weird. so it's kind of like overloaded. Merge can take either a set of vertices of G itself, which was this union of U, or it can take a set of vertices from this, and it will not very interesting.
Merge comma D you should give, right?
Yeah, that D is 1. So that D is always the D which was, for every DAG we have the special node, right?
So it's D.
Yeah, D. Okay. So this is merge as of now. Okay. So, but suppose this had not happened. In this graph, U is nil. That is, every vertex is reachable. Okay. The claim is, I take this merge of union of U and I subtract D. Okay.
1.
Yeah, I subtract 1. I get 7, 8, 9, 10, 11. And those are exactly the vertices. What did I delete? I deleted 7, 8 here. If I had deleted 7, 8 here, this is the set of those vertices, right? The claim is the complement of this set is an SEC, and that SEC contains D. Oh, sorry, that SEC, yeah. Sorry, what am I saying? Yeah.
So 1 out is still 1 out. It's not 1.
Yeah.
So we look at G. In G we had an edge to okay, I think I made some mistake in drawing this.
Are you sure you don't need the upward reachability from D out?
D.
No.
I mean, there are a bunch of vertices which if we just do downward reachable, then we'll have all vertices which are reachable from one.
So we have
One
okay.
may not be reachable
Okay.
from all those vertices.
What is this? Yeah, this is what it is. Yeah. So okay, let's. I probably messed up in the diagram somewhat. I'll basically state the claim. Okay. What mistake did I make here?
What is the, can you just mention it?
Yeah. So the claim is, there are like 3-4 claims. I thought I'll directly go to the last claim. Done. Okay. So let's go. Okay. So now let's do the other overloading of merge. Let's not take this union. Let's take merge of U. Okay. So what was U? I believe maybe deleting 7, 8. It's still not. It does decompose. Okay, let's take this. So U was a bunch of vertices.
So you are not starting with an SEC line.
No,
It's taking the one.
no, doesn't matter.
I don't see how. Okay, anyway.
So take U. U is a set of vertices in G prime which are not reachable from 1 out. Okay, they were some suppose. Okay, I'll have some. Okay, let's have some other sources that will make life easier. 10, 12. Okay. Suppose I had this extra source here, 12, which goes to 13, which goes here. So the SEC here is just 12 and 13. right? So all this is intact. I keep the rest of it same. I just have this extra appendage here. So now I call, now what is downward reachable of D out? All of these vertices were reachable. It's just these two vertices are not reachable. Okay. So U is 12 and 13. Okay. So now what is merge of U? Merge of U is just replace. If there is a one in or a one out, replace it. It's not. So merge of U is same as U. So it's again just U. Merge of U is U. Okay. So the elements of merge of U. So the claim is all elements of merge of U form separate SCCs in G. Okay, this is the first claim. Yeah, each of them is a maximal SCC in G. So
Merge of U.
every element of this is a subset of vertices of G, right? So each of those subset is a maximal SCC in G.
I don't understand.
No, we will get to this. Okay, so the claim is not clear.
It's just set of meta nodes, right?
Use a set of meta nodes. Each of those meta nodes corresponds to a subset of vertices in G.
Yeah, and you're saying that they are.
Each of those subset forms a maximal SCC in G. So 12 is a maximal SCC in G, 13 is a maximal SCC in G
Okay, before splitting.
before splitting
Okay.
in G. Yeah,
Of course, they form an ACC because
maximal SCC. Oh, see, yeah, so what you said?
from the ACC you are condensing it. So in the
Okay.
condensed graph, your nodes, you are the nodes from the condensed graph. So every node in a
Exactly.
you is the ACC.
So this is one way. It's very clear that every node here.
Some of the nodes will not be, some of the SEC we get in the condensed node won't be an SEC. in
No,
that. So-
every node will be an
It will be
SCC.
reachable from one.
Yeah.
So that is why this claim is.
We'll look into it. So the second claim is
Only SCCs which will change, like the only SCCs which won't be SCCs before splitting will be
The ones we
The
get
one-
from one out.
yeah.
So,
Basically, one SCC will split into some different SCCs and the other SCCs will not be there. You just like 2 and 3 is reachable from one.
this corresponds to
Because they are not, they were not in the, they were not in one SCC.
yeah. I'll read the claims. I'll just write it. I was hoping to not do these claims one by one, but okay, let's do this. Yes. Sorry. Okay. Yeah.
Stop the video recording in 2 minutes. But you can
Okay.
continue after.
Fine.
So we just write down the claim and then we'll stop the video recording.
Okay, so the claim is done.
Oh, the claim is.
Yeah. So the proof of this claim is the end of the
Okay, let's stop the
today's
record-
end.
Okay, let's stop the recording.
Okay.